What if the edge of our solar system isn't a graveyard of ice and forgotten debris, but a dormant genetic vault, a biological archive containing the frozen seeds of life itself? What if everything we've assumed about the origin of life on Earth has the story precisely backwards? Today, we step to the very boundary of the known cosmos to investigate one of the most extraordinary questions in the history of science. Is the Oort Cloud the galaxy's backup biological resource? And are we simply one of its delivery addresses? To understand this investigation, we must first journey back to 1950, when Dutch astronomer Jan Hendrik Oort was puzzling over a mystery that had nagged astronomers for decades. Long-period comets, those that swing through our inner solar system on orbits lasting thousands or even millions of years, were arriving from all directions with no obvious source. Oort proposed a solution: a vast spherical shell of icy bodies surrounding the entire solar system at distances so immense that the Sun, from that vantage point, would be barely distinguishable from any other star. This shell, what we now call the Oort Cloud, begins roughly 2,000 times Earth's distance from the Sun and extends nearly a quarter of the way to Proxima Centauri, our nearest stellar neighbor. It contains an estimated 1 to 2 trillion icy bodies, relics from the earliest moments of solar system formation 4.6 billion years ago. We have never directly imaged it. Its existence is inferred entirely from the comets it sends our way. And yet, remarkably, it may be the most important structure in the history of life as we know it. Here is where the story takes a profound turn. The Oort Cloud is extraordinarily cold. Temperatures hover between 4 and 10 Kelvin, within a handful of degrees of absolute zero, the coldest temperature physically possible. For most purposes, that sounds like a place where nothing could survive. But consider this. At those temperatures, chemistry essentially stops. Organic molecules, amino acids, even simple cellular structures would be locked in perfect stasis, their decay processes frozen to a standstill. Far from being hostile to life, those conditions are, in a very real sense, ideal for preserving it across billions of years. Research confirms that thin layers of ice, just a few meters thick, can absorb significant doses of cosmic radiation, shielding organic material embedded within comet nuclei. Data from the European Space Agency's Rosetta mission, which spent 2 years orbiting comet 67P from 2014 to 2016, detected glycine, the simplest amino acid, along with phosphorus, organic compounds, and complex molecules on a single comet nucleus. This was not an anomaly. When NASA's osiris-rex mission returned samples from asteroid Bennu in 2023, scientists found nucleobases, specifically cytosine and uracil, the very components of DNA and RNA, along with amino acids embedded in the rock. This is the argument that astronomers Sir Fred Hoyle and Chandra Wickramasinghe began advancing in the 1970s and 1980s, the theory of cometary panspermia. They proposed, controversially at the time, that life's building blocks, and perhaps dormant life itself, are distributed across the cosmos via comets and icy bodies. Earth, under this framework, is not the author of its own biological complexity. It is a recipient, a fertile landing zone for seeds dispersed from an interstellar reservoir. The Murchison meteorite, which fell in Australia in 1969, was found to contain more than 70 distinct amino acids, the vast majority of which do not occur naturally on Earth. A rock from space, carrying the ingredients of life, history recorded in stone. But how does this frozen archive actually deliver its cargo? That is where the mechanics become extraordinary. The Oort Cloud is not static. Two forces periodically disturb it, sending comets plunging inward toward the Sun and occasionally toward Earth. The first is galactic tides. As our solar system orbits the center of the Milky Way, completing one full revolution approximately every 225 to 250 million years, the gravitational gradient of the galactic disk pulls and flexes the outermost reaches of the Oort Cloud, loosening comets from their billion-year orbits. Astronomers estimate galactic tides alone account for roughly half of all long-period comets we observe.
The second trigger is passing stars. Throughout the solar system's long galactic journey, nearby stars occasionally drift close enough to gravitationally disturb the Oort Cloud. And here is a fact that transforms this from theory to mere certainty. The star Glace 7010, a dim orange dwarf currently about 63 light-years away, is on a confirmed approach trajectory. In approximately 1.3 million years, it will pass within 1/10 of a light-year of our Sun. That near miss will send a comet shower into the inner solar system, unlike anything that it has experienced in its recent geological history. This is not speculation. It is a calculated, confirmed future event.
What makes this mechanically elegant is the mathematics. Harvard astrophysicist Avi Loeb and colleagues have modeled panspermia mathematically as a contagion-style spread through stellar clusters, finding that life-bearing material can transfer between neighboring solar systems at surprisingly high rates during the early, closely packed phase of star formation. Apply this to the Oort Cloud framework, and the conclusion becomes striking. Life, once seated anywhere in a spiral arm of the galaxy, could propagate across that arm within a few 100 million years. Not through spacecraft, through gravity, through the slow, inevitable mechanics of orbital disturbance and interstellar transfer. But what protects this cosmic library from destruction before delivery? This is where the Oort Cloud's architecture becomes its most remarkable feature. Think of it as a redundancy drive, the information technology concept of a backup system that preserves critical data through any local failure. While the inner solar system is periodically sterilized by catastrophic events, large impacts, nearby supernova shockwaves, gamma-ray bursts, the Oort Cloud's extreme distance and dispersal insulate it. A gamma-ray burst powerful enough to strip Earth's ozone layer would dissipate long before reaching the dilute, scattered material of the outer Oort Cloud, with sufficient energy to destroy organics shielded inside icy nuclei. The evidence for extraordinary biological resilience reinforces this picture. In 1995, researchers reported culturing viable bacterial spores from 25 to 40 million-year-old Dominican amber. A controversial 2000 study claimed revival of bacteria from 250 million-year-old Permian salt crystals. Theoretical models from astrobiologists at the University of Edinburgh suggest microbes fully embedded within comet nuclei could remain viable for timescales approaching 1 billion years. And in 2019, we inadvertently tested this ourselves. When Israel's Bereshit lunar lander crashed on the moon, it scattered thousands of dehydrated tardigrades, microscopic animals capable of surviving near absolute zero, intense radiation, and the vacuum of space across the lunar surface. Scientists confirmed they likely survived the impact. Humanity had, entirely by accident, conducted its first act of panspermia. The irony should not be lost on us. There is also a profound and paradoxical pattern embedded in Earth's own geological record. Paleontologists have identified a roughly 26 to 30 million year periodicity in mass extinction events. Astronomer William Napier of the Armagh Observatory has connected this rhythm to galactic tidal cycles, the same forces that disturb the Oort Cloud. The same comet showers that delivered catastrophic impactors capable of ending entire epochs of life may simultaneously have delivered fresh biological material. The mechanism that destroys also restocks. Life, it seems, has been editing and reseeding itself through the same gravitational heartbeat of the galaxy for billions of years. Perhaps the most intimate evidence for all of this is written into your own body. Approximately 8% of the human genome consists of sequences that are not originally human. They are integrated viral sequences, remnants of ancient infections, permanently embedded in our DNA across millions of years of evolutionary history. The genome is not merely a blueprint, it is an archaeological record. Every major biological input, every ancient encounter, is documented in nucleotide code. Now extend that principle outward. If cometary deliveries contributed biological material to early Earth, some of that interstellar authorship may already be written into the deepest foundations of terrestrial life. There is one additional clue that scientists call the chirality problem, and it is, frankly, a smoking gun. All life on Earth uses exclusively left-handed amino acids. Chemistry, when producing amino acids randomly, creates equal quantities of left-handed and right-handed versions. There is no known chemical process that should favor one-handedness exclusively on a planetary scale. But if life arrived from a single cometary source that had already established this chirality, or from a common interstellar chemistry that consistently produces the left-handed variant, the uniformity makes perfect sense. Recent James Webb Space Telescope observations, published through 2025 and 2026, have confirmed the presence of complex organic molecules, including precursors to amino acids and phosphorus-bearing compounds, in star-forming molecular clouds throughout the galaxy, environments where proto-Oort Cloud material would have originally formed. The building blocks are not rare. They appear to be a standard feature of how the universe assembles itself. This brings us to what I believe is the most profound reframing in the entire investigation. For centuries, we have looked at the sky and asked, are we alone? But that question assumes Earth is the starting point. What if, instead, we are one of billions of test sites, seeded by the same interstellar reservoir, running the same biological experiment at different stages of development? The ESA Comet Interceptor mission, targeted for launch in 2029, will intercept a dynamically new comet making its very first pass through the inner solar system. Pristine Oort Cloud material, never before heated by the sun, available for direct chemical analysis. Scientists have specifically designed its payload for biosignature detection capability. A proposed NASA interstellar probe would travel beyond 1,000 astronomical units into the heliospheric boundary and the inner Oort Cloud itself, carrying instruments capable of detecting organic and isotopic biosignatures directly. When those results arrive, they may confirm what the mathematics, the chemistry, and the biology have been quietly suggesting for decades: that the Milky Way galaxy is not an accidental host of isolated life events. It is a self-sustaining biological system, a distributed, self-replicating network in which comets serve as the connective tissue, gravity serves as the delivery mechanism, and the Oort Cloud serves as the archive that outlasts every catastrophe. History, in my view, is never simply about dates and events. It is about the moments when humanity is forced to fundamentally revise its understanding of its own place in the cosmos. The Copernican revolution told us Earth was not the center of the solar system. Darwin told us life was not fixed. And now, piece by piece, From the organic chemistry in a meteorite to the genetic echoes written inside every living cell, a new revolution is taking shape. We may not be the origin of life. We may be the galaxy's most recent experiment, and the first one to realize it. What does that change about how you see the night sky? I'd love to know your thoughts in the comments below. And if this kind of deep historical investigation resonates with you, there is much more waiting to be explored. I'm Arthur Winslowe, and history, in all its forms, is never finished with us.